Chapter 4, Overview of Protein Structure. Conformation is the spatial arrangement of atoms in a protein or any part of a protein. Proteins tend to have a few different conformations. Proteins in any of their functional folded conformations are called native proteins. Some proteins lack discernible structure and are called intrinsically disordered proteins, but are totally functional. There are supersecondary structures, folds, and motifs which are important in protein conformation. A protein's conformation is stabilized largely by weak interactions. Stability is the tendency to maintain a native conformation. Native proteins are only marginally stable. Unfolded proteins are kept unfolded by a high degree of conformational entropy and by hydrogen bonding interactions with the solvent, water. However, folded proteins are kept folded by disulfide or covalent bonds and non-covalent interactions. That is, hydrogen bonds, hydrophobic effect, ionic interactions. Many proteins lack disulfide bonds. Most intracellular environments are too reductive. Extracellular environments tend to be oxidative. Weak interactions are important for the folding process. Even though weak interactions are far weaker than covalent bonds, they are more numerous and therefore are a leading factor in protein stabilization. The net stability of the transition between unfolded and folded states may be close to zero, because although bonds form in the transition, they also break. The hydrophobic effect generally predominates in protein stability. When water surrounds a hydrophobic molecule, the optimal arrangement of hydrogen bonds causes a solvation layer, which is a highly structured shell of water around the molecule. Although this orderliness is an unfavorable decrease in entropy, the molecule's nonpolar groups cluster together, decreasing the extent of the water layer, causing an overall increase in entropy. This increase in entropy is the major driving force of the clustering of hydrophobic groups in water. Entropy is also the major driving force of the formation of hydrogen bonds in polar groups of proteins. There is a solubility limit to even the most polar molecules, as their presence causes a net decrease in hydrogen bonding per unit mass. Therefore, a solvation layer forms to some extent even around polar molecules. Most of the net charge and free energy, as nonpolar amino acid side chains aggregate within a protein, is therefore derived from the increased entropy in the surrounding aqueous solution, resulting from the burial of hydrophobic surfaces. Hydrogen bonds form cooperatively. If one hydrogen bond forms, the next is more likely to form. Salt bridges may either stabilize or destabilize a protein. However, salt bridge strength increases with decreasing dielectric constant, and the protein interior has a much lower dielectric constant than does the solvent. So, salt bridges can provide immense stability. They also imbue a protein with definite structure, which random clustering of nonpolar groups via the hydrophobic effect and the entropic effect cannot do. Van der Waals interactions also help stabilize proteins, but they too are weak. They are dipole-dipole interactions. Two main rules of protein folding. 1. Bury the hydrophobic groups because entropy. 2. Maximize the number of non-covalent interactions. The peptide bond is rigid and planar. Covalent bonds matter. The atoms of a peptide bond are coplanar, and resonance exists between the carbonyl oxygen and the amide nitrogen. Due to this resonance, that is partial double bond character, the carbon-nitrogen bond cannot rotate freely. Only the alpha carbon bonds can rotate. The oxygen has a partial negative charge, and the hydrogen bonded to the nitrogen has a partial positive charge, causing a slight dipole. Peptide conformation is defined by three dihedral angles: phi, psi, and omega. Phi involves the nitrogen alpha carbon bond. Psi involves the alpha carbon-carbon bond. Omega is often ignored, but involves the carbon-nitrogen bond. Phi and psi angles theoretically can have any angle between negative 180 and positive 180, but steric interference prohibits some, for example both phi and psi having 0. In a Ramachandran plot, psi is plotted versus phi. Protein secondary structure. Secondary structure is the local spatial arrangement of the main chain atoms of a chosen segment of a polypeptide chain without regard to its side chains or its relationship with other segments. Regular secondary structure is when the phi and psi angles remain nearly constant throughout the segment. Common secondary structures are alpha helices, beta sheets, and beta turns. The alpha helix is a common protein secondary structure. Angstrom is a unit measuring distance. The R groups of the alpha helix protrude outward. The helix turns every 5.4 angstroms, and each helical turn includes 3.6 amino acid residues. Right-handed alpha helices are more common. The alpha helix is so favorable because of the internal hydrogen helical bonds. The hydrogen atom attached to the electronegative nitrogen atom of a peptide linkage forms a hydrogen bond with the electronegative carbonyl oxygen atom. Each turn involves 3 to 4 of these bonds. The last few amino groups of the helix cannot participate in this hydrogen helical bond, so they form hydrogen bonds with the surrounding water. All amino acids must be either D or L in a helix. Amino acid sequence affects stability of the alpha helix. Some amino acids are more likely to form alpha helices than others. Alanine is the most likely, and amino acids with greater delta-delta G0 are less likely to form alpha helices. Proline is the least likely because the nitrogen atom is part of the R group's rigid ring, not allowing nitrogen alpha-carbon bond rotation. Interactions between amino acids also affects the helix stability. Examples: an alpha helix composed only of amino acids with negatively charged or positively charged R groups will not form because they will repel each other. An alpha helix with bulky amino acids too close to each other will not form. Critical interactions between amino acid side chains occur 3, sometimes 4 residues away. Proline isn't likely to appear in an alpha helix for the reason given above. Glycine is also infrequently included, but because it has more conformational flexibility than the other amino acid residues, so glycine takes up coiled structures different from alpha helices. Peptide bonds have a slight dipole, and these accumulate along the alpha helix, such that the N-terminal has a slight positive charge, and the C-terminal has a slight negative charge. So in order to stabilize this polypeptide, negatively charged amino acids are found on the N-terminal, and positively charged amino acids are found on the C-terminal. Summary of 5 things that affect alpha helix stability. 1. Whether the amino acid wants to form an alpha helix. 2. Whether the amino acid wants to form an alpha helix next to that other amino acid, especially 3 or 4 residues away. 3. Bulkiness of adjacent R groups. 4. The presence of proline and glycine. 5. Whether the amino acids at the positive N-terminal and negative C-terminal really belong there. The beta conformation organizes polypeptide chains into sheets. Hydrogen bonds form between adjacent segments of the polypeptide chain within the sheet. Adjacent polypeptide chains in a beta sheet can be either parallel or anti-parallel, having the same or opposite N to C terminal orientations. The repeat period, that is, from one trough to another trough of the pleated sheet, is shorter for parallel conformation. 6.5 angstroms for parallel, 7 angstroms for anti-parallel. The hydrogen bonds of parallel sheets are not aligned perfectly, whereas they are aligned in anti-parallel sheets. Beta turns are common in proteins. The polypeptide chain may reverse direction. Beta turns connect 2 anti-parallel beta sheets by a 4 amino acid turn. The carbonyl oxygen of the first residue forms a hydrogen bond with the hydrogen of the amino group of the 4th residue. Glycine and proline are often found in beta terms. Glycine occurs because it is small and flexible. And proline occurs because the amino nitrogen in the ring structure readily assumes the cis configuration. Beta turns are often found near the surface of a protein so that it can form hydrogen bonds with water. There are also gamma turns, which involve 3 residues. Common secondary structures have characteristic dihedral angles. A Ramachandran plot is good at predicting phi and psi angles, and therefore secondary structure, but glycine can assume many conformations that are sterically forbidden for other amino acids. Common secondary structures can be assessed by circular dichroism. Circular dichroism, CD spectroscopy, is characterized by differences in absorption between right-handed versus left-handed circularly polarized light due to the asymmetry of a molecule. The alpha helix, beta sheet, and beta turns have characteristic CD spectras. Protein tertiary and quaternary structures. Tertiary structure is the overall 3D arrangement of all atoms in a protein. Think of it as the sum of secondary structures. Quaternary structure is multiple tertiary structures, that is, multiple polypeptide chains, or subunits, identical or different. 2 common higher-order structures are fibrous proteins and globular proteins. Fibrous proteins usually consist of one type of secondary structure, whereas globular proteins usually involve multiple types. Fibrous proteins are often support proteins, and globular proteins are usually enzymes and regulatory proteins. Fibrous proteins are adapted for a structural function. Fibrous proteins have lots of hydrophobic amino acids, and so are insoluble in water. Alpha-keratin. Alpha-keratins constitute hair, nails, and more. They are a part of the intermediate filament, or IF, protein family. The alpha-keratin helix is composed of 2 right-handed alpha helices, forming a super-twisted coiled coil, which is left-handed, increasing strength. The superhelix is left-handed because the right-handed helices coil around each other in a left-handed manner. Disulfide bonds strengthen the quaternary structure of alpha-keratins. Box 4.2. Waving or curling hair involves exposing the hair to moist heat, thus stretching the alpha helices into a beta conformation around a certain shape, adding a reducing agent to break disulfide bonds and break hydrogen bonds, adding an oxidizing agent to form new disulfide bonds, washing the hair, and cooling it. Collagen. Collagen also provides strength to connective tissue, tendons, cartilage, and more. The collagen helix is 1, not an alpha helix, 2, left-handed, and 3, has 3 amino acid residues per turn instead of the alpha helix 3.6 residues. Collagen is a coiled coil composed of 3 alpha chains, not helices. This superhelical twisting is right-handed, opposite of the alpha chain left-handedness. In other words, each left-handed coil coils in the right-handed direction around the other left-handed coils. The collagen amino acid sequence is typically glycine XY, where X is proline and Y is 4-hydroxyproline, 4-hype. Box 4.3. Scurvy is caused by vitamin C deficiency. Vitamin C is needed for the hydroxylation of proline and lysine in collagen. So, a vitamin C deficiency deprives collagen of 4-hydroxyproline. Silk fibroin. Fibroin is the protein of silk, and it contains chains predominantly in the beta conformation, held together by weak interactions, allowing it to bend. We'll pause here.